Hey, what is going on? It is Friday, January 28th, 2022, and it is snowing outside. Yes, it is very snowy. Well, not very snowy yet, but supposedly there's supposed to be a blizzard today at some point. I thought it was coming in the evening, but it might come earlier. Who knows? Whatever the case is, probably not the greatest day to travel if you're on the road, so don't be too ambitious with your driving plans if you're in the area that I am, at least. But either way, we're not here to talk about snow. We're here to talk about hemoglobin. All right, yes, it's snow is white and hemoglobin is red, almost like the exact opposite intensity of color. I probably use those words in the physics sense wrong, but who cares? So anyway, yeah, and we're gonna be wrapping up our series on hemoglobin, and I think the last thing I actually will do, there's one more that I will do, is probably go into the actual blood cell life cycle, red blood cell, erythrocyte life cycle a bit, because that's actually important to really round out the studies, because you know, it goes, the next step would be the red blood cells, understanding, where the hemoglobin is, and then moving up to the cardiovascular system. And that's kind of the trajectory I wanted to take before delving back into biochemistry on the immune system level. And I'll decide then what's the next step. But this was an important series of lectures because this kind of set up the understanding and foundations for how red blood cells operate, which is important ultimately to understanding or figuring out the secret of eternal life. Okay, so let's get to it. Hemoglobin is susceptible to disease, right? And it's susceptible. Abnormal hemoglobin will cause disease in a person's body. So the most well-known disease, most famous disease that is implicated or caused by abnormal hemoglobin is called sickle cell anemia. And most people knew about this because in the 90s it was quite popular in the news when people learned about how sickle cell occurs and learned about the effects it has on certain populations and how to treat it. So essentially, sickle cell anemia is interesting because it's very visual as to what happens, right? I guess many diseases have visual representations that are easy to see, but sickle cell anemia is very clear, even under a microscope what's going on, right? Like if you look at the sickle cell images, the red blood cells that are sickled, so to speak, are visibly distorted under stain, under a blood stain. So essentially, what is causing this sickling, right? What is causing this distortion, and what implication does the sickling have on the rest of the system? Okay, so basically it only happens, let's start with the hemoglobin. So the sickling occurs because of the formation of hemoglobin polymers, right? So hemoglobin has 4 subunits, which the alpha 1, beta 1, alpha 2, beta 2, which they are supposed to stick to each other and form a single hemoglobin unit. And that's it. That hemoglobin unit is supposed to act in solitude and bind oxygen, as we've talked about, to its heme groups and continue releasing oxygen to tissues, again, in isolation. But what happens with sickle cell anemia is that the hemoglobin starts to bind together into fibrous chains. And the reason for that is because the hemoglobin has been essentially mutated. Okay? I'm looking for a good image of this, but the hemoglobin has been mutated. So essentially, polymerization of the hemoglobin subunits will occur. Okay, so how does this happen, right? So this is a good representation. So the hemoglobin essentially suffers, the beta chain suffers, the gene that codes for the beta chain. Remember, there's genes that code for each of the globulins that are part of the hemoglobin, right? The gene that codes for the beta chain actually has a point mutation that on its sixth amino acid. Um, and the sixth amino acid point mutation is a single substitution of a valine amino acid, a glutamate amino acid for a valine amino acid. So, what is the reason? How does this occur? Okay, so again, and why is this a problem? Okay, so normally the glutamate that appears in this beta subunit is a polar molecule. Okay, and this polar glutamate will interact with water, right? Because it's polar, so it'll interact with other polar molecules and thus create a solvation barrier. Okay, so what does that mean? So that solvation barrier prevents hemoglobins from sticking to each other, adjacent hemoglobins. But what happens when we use when we have a substitution for a non-polar valine, right, due to a point mutation in the genetic code of the hemoglobin? What happens is then the beta subunit ignores it becomes hydrophobic, so it doesn't want to deal with the polar water molecules. And what will happen is it will, through amino acid interactions, actually interact with either an exposed I forget the exact, it's a phenylalanine, right, a phenylalanine amino acid on the 85 chain, or the 85th phenylalanine, or 88 leucine, or even another valine. I believe, I've heard it being referred to as another valine. Either way, what will happen is there will be an cross globulin interaction between the beta subunit of one hemoglobin with the beta subunit of another hemoglobin, and these interactions will essentially be aggregated together because these betas will interact with these betas will interact with these betas, and so on and so forth, and then they will form these long fibrous chains. So why is this a problem? Because the long fibrous chains actually become so thick that they lead to this sickling. Like these normal red blood cells have the hemoglobin flowing around them in relatively free way, as opposed to the long fibrous polymers that occur in the sickle cell. And what happens at that point is then this sickle cell, as you can see here, this is a good descriptor. These sickleized cells, due to this polymerized hemoglobin, will block arteries or block the blood vessels, and will start to cause painful clogs and restrict blood flow to certain places, causing tissue anoxia. Okay, tissue anoxia means the loss of or lack of oxygen, right? And tissues need oxygen to survive, so these are called infarctions, right? So whenever you have the lack of substance going to where it needs to a particular tissue, you have infarctions. Like for the heart, you would have a stroke of the heart due to lack of efficient blood flow there. You have a myocardial infarction. In this case, you would have blood vessels, smaller scale blood vessel or capillary infarctions, which will cause localized tissue death, and which will lead to pain in those areas because your tissue is dying. And this will also cause infections, right? Because remember, in your blood, what happens? Antibodies also flow. Other white leukocytes also flow, like macrophages, neutrophils, and if they can't get to where they are going because of clogged capillaries due to sickle sickleized cells blocking the capillary egress, then they won't be able to effectively get to bacteria that are on another side of your body, or on some sort of infection that's on another side of your body, and thus your resistance to infection will go down. Okay, so that's another thing. Sickle cell is actually quite a bad disease in many ways. Like, And here's yet another reason, another issue with sickle cell is that, remember, sickle cell only occurs in, and this is like the entire chart, by the way, what we were talking with the coding sequences. This is the change of the amino acid here. To the mutant has valine hemoglobin S. The issue with sickle cell is that sickle cell affects deoxyhemoglobin, right? So hemoglobin that doesn't have oxygen bound to it. So that means that whenever you have a situation where you have essentially elevated oxygen available to your tissues, remember, due to high altitude exposure, which increases your BP2-3 BPG levels, whenever you're exercising, right, and whenever you need to release oxygen, you can't, because you have more deoxyhemoglobin, and therefore more of the hemoglobin and thus red blood cells become affected, and the red blood cells sickleize, right? So anytime you exercise, you lead to symptoms of sickle cell anemia. So that means you can't exercise, and lack of exercise leads to other conditions in your body, unhealthy conditions in your body, right? Poor health. So that sickle cell anemia is actually, if you think about all the issues with it, it can be a bad disease. It's a very clearly demotivating disease, random pains, and just lots of inability to exercise, random infections, and basically the way people treat it. And oh, by the way, sickle cell anemia is one of those things that manifests when you get older also, right? Because remember, it affects beta chains, beta globulins, but it doesn't affect fetuses, because fetuses, and I guess when you're younger for a while, have gamma globulins. Gamma globulins are, remember, the substituted globulin subunit in the hemoglobin for fetuses, and hemoglobin F, right? So, as you get older, you'll experience more of the symptoms of sickle cell anemia. So, how do you treat it? There's lots of different treatments for it, but essentially, what you have to do, right, is you have to prevent the hemoglobin from binding to each other, right? And one of the ways that that's done is through the use of a drug called hydroxyurea, which is an anti-tumor drug. Okay, this is actually a better image. The hydroxyurea has essentially prevents the binding of the subunits, or the aggregation of by connection of the valine to of one subunit to the valine or phenylalanine or leucine at those specific 88 positions in the other hemoglobin's beta subunit. So that's one way you treat that, by causing the sickle cell. The hydroxyurea causes the actual sickling of the cells through less aggregation of those hemoglobin. Another way you can do it is through drinking water. That's probably one other way, right? Like being hydrated, and I guess you have to be hydrated quite often, increases the separation of the hemoglobin, the natural separation of the hemoglobin within blood cells, and prevents the sickling, and thus prevents the aggregation of alternating hemoglobin, because it kind of keeps them away. Because I guess the pressure of the other amino acids on hemoglobin, on the hemoglobin, or the other hydrophilic amino acids on hemoglobin to the water, will somewhat keep the culprit amino acids from interacting with each other. And the other thing to do is you need antibiotics pretty often, which suck because they have their own side effects. Antibiotics are needed because, again, increased infection potential is a result of the sickling due to the inability of antibodies and other immune cells to get to where they need to, aka the site of an infection. So again, another thing to think about just quickly is, why does this occur in hemoglobin, deoxyhemoglobin, and not oxygenated hemoglobin? Well, in deoxyhemoglobin, your those amino acids, those culprit amino acids, are exposed and thus can easily interact, cause the hemoglobin beta chain to interact, or beta subunit to interact with an alternate hemoglobin beta subunit. But with the deoxyhemoglobin with oxygen added, the those amino acids, those implicated amino acids, are no longer exposed and thus can't interact with each other. So in a way, you could say that's a saving grace, because if the oxygen just didn't happen to prevent the exposure of those amino acids, the binding of oxygen, then I'm sure a person would die much faster, because there would be a lot more sickling in your body, even in oxygenated hemoglobin and oxygenated tissue. So that's, yeah, I mean, that's that. Kind of hate to end on a sour note. And also, there's other, I guess, a positive, sort of positive, note is that there's other hemoglobinopathies which have other less intense or less harmful diseases associated with them due to amino acid substitution. So again, another genetic one is the hemoglobin C formation, which causes the amino acid to, instead of turn, the mutant amino acid isn't a valine anymore. It actually becomes, what was that amino acid? It becomes a polar amino acid, not a non-polar amino acid, which is, it becomes a positively charged amino acid, and that positively charged amino acid actually isn't so bad, because it still won't result in the aggregation of hemoglobin, so you won't get the sickling of cells, but you will get some hemolytic anemia, meaning that your blood cells will die quicker for some reason. In sickle cell anemia, your blood cells die quickly anyway, so that's essentially a problem either way. So yeah, I think that's about it. There's quite a bit to actually talk about in this realm, but I wanted to leave this fairly high level. And yeah, I will, the next time we see each other and talk, we'll be talking about the life cycle of a red blood cell, and maybe some stuff on blood vessels. So that's it for now. Thanks for listening, and we'll see you around.